So in a previous video I showed you how to generate a structure file for urea, and this gave us a result with 14 neighbours, which we can see here. So 14 was quite a bit more than what we used in our published calculations. We actually used 10 neighbours. And I'll just show you how you actually generate a structure file with 10 neighbours. So what we're actually trying to achieve is we need to remove 4 of the weakest interactions that have been added to these urea molecules. So what we need to do first is to recalculate the adjacency matrix that we generated our structure files from, because we need to recalculate which things are actually neighbouring molecules. So let's go back to the urea we had originally. So if I just visualise this quickly, you can see this is the same one that we started from, with a lot of van der Waals interactions between carbons and hydrogens on neighbouring urea molecules. So the first thing you want to do is create a duplicate of our previous calculation, because we don't want to lose what we did before. So you just right click and press duplicate, and then you can rename the new entry to something else. So I'll call this urea 10, as we're trying to generate a structure file with 10 neighbours. Now we need to recalculate the adjacency matrix. So I'll just quickly run through what I did last time again. So we've got a result to compare to. So I opened AutoCN, I went to options, matrix, and I just had everything as default. So the method of calculation, I use domains. I'll talk about what these other ones mean later on in this video. And I left this minimum omega as 1.5. So this minimum omega parameter is crucial, as I said in the previous video, as this will decide the strength of the interactions to consider as actual intermolecular bonds or intermolecular interactions. So the higher this number is, only the stronger interactions are considered, so it'll cut off weaker ones, and the lower the number is, the more weaker interactions it'll consider. And this number itself, the actual omega it mentions, is the solid angle. So the solid angle is related to the face size of the Voronoi polyhedron that you're calculating for your molecule. So larger omega means larger face, so it'll only consider stronger interactions. Smaller minimum omega means it'll consider smaller faces, which means weaker interactions. So this is what we had previously, so I'll just run it again so we've got some results to look at. So we have a lot of van der Waals interactions here, 4, 6, 2, 2. So let's see what happens if we increase minimum omega. So I'll go back to matrix, and I'll change this from 1.5 to 5. Press OK and run. You can see this number's decreased dramatically. It's gone down only to 2, 3, and we've lost the interactions from the carbons, nitrogens and oxygens. So this might be a good candidate for getting our 10 neighbours. So if I close that, press yes to removing the results, and I'll recalculate our simplified net using ADS. So I'll just leave everything the same as last time, same parameters, and I'll press OK and press run. And using the whole molecules as the centers of the net again, and we've generated our structure file. So if I view this file, you can see we've reduced down to our 10 neighbours. So I can then export from the database as I did before to get our matching bonds file for urea. So I'll export that to our tutorial database folder, call it urea 10. Then I'll navigate to my file explorer window to the folder containing these files that I've generated and open them in a text editor. And then we can compare them side by side. So you can see we've got 10 lines here this time, 1 to 10. We've got 6 interaction types. Then we've got 6 interaction energies down here, which will require adjusting. So there might be cases where you want to generate lots of different representations of your crystal structures with different interaction strengths. And going back through and changing the minimum omega over and over can be quite time consuming. There is a shortcut, but it can only be used sometimes. You have to be quite careful when you use it. So the first thing I'm going to do is create a duplicate of our original urea calculation where we had 1.5 as our minimum omega when we were calculating the adjacency matrix. So we're going to start from a description which has a lot of intermolecular interactions, a lot of these van der Waals interactions, and we're going to reduce that down in steps and see what we can create. So if we go to compound, generate representations, we get this window here. So what this is going to do is it's essentially running AutoCN over and over with different minimum omega values put in. So we can say that we want to consider hydrogen bonds and van der Waals because we know those are there, and we can use the solid angles method of calculating this adjacency matrix. It's not exactly the same as the domains method, but they are very close to each other. So as long as you check your files and just to make sure that they make sense, this method can help you generate a series of structure files with reducing interaction strengths considered. So it can be quite useful to use this approach when you're not sure exactly of which interactions to consider. So this minimum interval is the step size that will be applied to minimum omega. So it'll increase in steps of 1.5 here. So I'll leave it as 1.5 for now. And this mode here, we want to remove bonds because we're starting from a description which has a lot more bonds than we want. We want to create duplicates of urea in the same database. We have to have this duplicate option selected. So we'll click OK, and you can see it's generated a series of interaction strengths, and you can see it tells you what the omega was set to when it generated those files. We can visualize some of these files to see what the differences are between them. So if I visualize this file, you can see we've got lots of van der Waals interactions between the urea molecules. If we go into the adjacency matrix, you can see that as well. If I expand all of these, a lot of van der Waals and a lot of hydrogen bonds. If we then jump to a much higher interaction strength, like this one, for example, 15.5, so you can see we've got no van der Waals interactions at all here, just hydrogen bonds between the hydrogens on the amine groups going to the carbonyl on your urea molecule. If we go to the strongest interaction strength, this 32% here, you can see we've started to lose our actual valence bonds. So our urea molecules are not even being constructed anymore. So it's cut off the valence interactions. So obviously that's too high. So we saw that 15.5 had no van der Waals interactions at all, but we do want to consider some of them, as we've done when we calculated our urea with 10 neighbours. So somewhere between 2.5 and 15.5. One of those representations is going to give us the bonding in urea that we want. So we want to calculate simplified nets for every single one of these. You can actually calculate simplified nets for more than one species in one go. By selecting 15.5, holding Shift and selecting 2.5, you can see they've all gone bold, which means they're all selected. And then we can click ADS and we can actually calculate our simplified net. We need to make sure we select options and go to this continuous tab here because we need to tell it which central atoms to look for. So we're actually not having any central atoms, so we need to delete that. And that's pretty much the same as clicking whole molecule every time it runs another simplification. So we'll click run, press yes, and you can see it's calculated all of those files in one go. So if we view each one of these in turn, you can see that's got 14 neighbours with 2.5 as the minimum omega. 8.5 has 10 neighbours. 13.5 has 6 neighbours, and 15.5 has 4 neighbours per molecule. We can also export multiple files out of the database in one go, but we have to make sure that your Topos parameters are set to output to multiple files. So we can do the same thing to select multiple entries as we did on the original database, where we hold Shift. They've gone bold, so they've all been selected. Press Export, and we choose the folder where we want to save them, which is this tutorial video folder. And then we can navigate to that folder in our file explorer. And you can see that all those files have been written out. So if I select them all to view in a text editor, you can see we've got different structure files with corresponding bonds or net.txt files we can use together. So this approach is more of a shortcut. It's not something that can be used every single time, but it's a good way if you're starting to look at a new structure to see which minimum omegas are key for switching off certain bonding interactions. Going back to our calculation where we had 10 neighbours for each urea molecule, we need to find out what these interactions actually correspond to. So these 1, 2, 3, 4, 5 and 6, what are they chemically? You can't say that 3 is a hydrogen bond from looking at it. You need something to visualize the structure with the interactions labeled with these numbers to help you locate them. But luckily there is a feature in ToposPro which lets you do that. So if we go back to our calculation here, so this is our urea with 10 neighbours where we've calculated the simplified net. So if we visualize that with IsoCryst, you can see we have our simplified net defined by these dummy ZA atoms overlaid on top of our original net, which contains the atoms that make up the molecules. So each of these dummy atoms, these ZAs, are going to be placed at the center of mass of each of our separate molecules. You can actually switch these to geometrical centers if you go to your ADS options when you're calculating your simplified nets. So you can change this to a geometrical center, but I've left it as mass for now. So if you want to switch back to IsoCryst, you click Program, click IsoCryst. So each of these central atoms is going to have bonds to neighboring central atoms. It's going to have 10 of them, which corresponds to the 10 that we've defined in our net.txt file. First, we want to get one isolated molecule and one isolated centroid. So we can do that by switching off van der Waals and hydrogen bonding interactions and clicking this Select Polymeric Chain option down here. If we click any atom on a molecule that's connected by valence bonds, now as we've defined up here, it'll select all of those connected species. And then if we go back to selecting a single atom, we can select one of these centroids as they're all linked by valence bonds, so we don't want to use Select Polymeric Chain there. Then we can click Show Selection Only, and it'll remove all the other atoms. So we can grow all the connecting centroids by selecting the centroid and then pressing Grow. So now we've got our 10 connected neighbours. And then if we want to fill in the actual molecules that are defined by these centroids, we can use that Select Polymeric Chain tool again and keep growing this molecule and keep selecting it until it's fully grown. So now we've got one molecule and 10 centroids. So now let's add all of the molecules that these centroids correspond to. So we can use the Polymeric Chain tool again. I should also mention that left clicking selects and right clicking deselects when you have the select option chosen up here. So I'll select this central urea molecule and I'll enable van der Waals and hydrogen bonds. So when I now press grow, it'll grow the first atom on the neighbouring species because they're connected through these van der Waals and hydrogen bonds. Now if I use the Polymeric Chain selection tool again and click the original molecule, it will actually also include these extra atoms on the neighbouring molecules. So if I turn off van der Waals and hydrogen bonds again, now it's restricted to growing through valence bonds. So I can grow again and it'll start to fill in the neighbouring molecules. So you can repeat this process a few times until you've grown your neighbours. If the centroids weren't present, we could just allow growth by valence bonds and just keep press and grow, but that would actually add extra connections to these neighbours as well, which we don't want. So now we've got our nice grown net with all of our molecules shown and all of our centroids shown. We can start to try and label these interactions. First, we need to select the bonds that we want to label. So if I use the polymeric chain tool again and select one of the central atoms, it'll highlight them all. Then we can go to this IsoCryst options button up here, and you can choose to apply a label to bonds. So you can choose bond distance, which will tell you the distance between the centroids of the molecules, or you can use this number here, which will correspond to that net.txt or the bonds file you generated for CrystalGrower. You can also apply a special color to the bonds as well to help you distinguish them. So I'll enable both of those and press OK. So you can see now that we've got numbers on each of these interactions. If I click this show bonds colored here, now they've all got a special color. So interaction type 1 is colored orange, interaction type 2 is colored yellow, interaction 3 is green, interaction 4 is a cyan color, and then interactions 5 and 6 are blue and light blue. And you can start to zoom in and actually look at what these interactions correspond to. If I zoom in here, you can see that there's matching pairs of interactions on opposing sides of the molecule. So we've got a pair of 1s on either side here, a pair of 2s on either side here, a pair of 5s on the bottom there, and a pair of 6s on the bottom too. And then you've got interactions 3 and 4 following along the C-axis of the crystal. So if I turn on the hydrogen bonds, we can start to see something chemically about the interactions here. So we can see that interactions 3 and 4 correspond to this pair of hydrogen bonds that are made with molecules along the C-axis. And in one direction it'll correspond to accepting a hydrogen bond, and one direction it'll correspond to donating a hydrogen bond. We can also see that there's a single hydrogen bond for interaction type 1. This may help us to make a decision about what energies to assign to each of these species. As I said before, we still need to consider the interactions with solvent. As we're going from solvent to crystal, we're calculating free energies of crystallization, so just because the bonds are stronger doesn't necessarily mean that they'll have higher free energies of crystallization. We can also then turn on the van der Waals interactions, and you can see which species those correspond to. It's a really useful way of finding out what your interactions in your net.txt or your bonds file correspond to. So we now know that 3 and 4 are pairs of hydrogen bonds, and 1 and 2 also have one hydrogen bond, whereas the rest of the interactions are van der Waals based. You can also manually edit the visualization of your bonds a little bit to improve your images. So as you can see here, the underlying net, I've actually recolored these bonds to be just grey, as sometimes the colouring of those bonds can actually distract from the colouring of the interactions. So to do that, you can just select polymeric chain again, click one of the molecules that are part of the underlying net, and move to edit bond. You can then choose a different colour, so I'll change these to like a dark purple colour just to test, and I'll press OK. So sometimes the bonds actually disappear, but if you press Ctrl Z, undo, the bonds will reappear with the colour assigned to them. So you can see these have all changed to this like dark purple colour, but I'll change them back to grey because that's a little bit clearer. Same thing happened again, but Ctrl Z brings them back. You can actually tidy up the simplified net too, so if we only want to see the connections to the central species, we can select all of the surrounding centroids by clicking on them with the selection tool. And then we can also use this edit bond and untick the visible option. Press OK. It'll hide those interactions. So it makes it a lot easier to see now. You can actually do the same for the van der Waals interactions between the neighbours too. So if I select these 3 atoms here, I can say edit bond and make this invisible too. And eventually if you go around you can tidy up your net a lot to make it much clearer. So that was a tutorial on using some shortcuts to generate multiple representations, how to output multiple files at once from Topos, and how to match your interaction type numbers with actual chemical interactions in your crystal structure. In the next video, I'll go through more advanced methods of creating your adjacency matrix.